Just over this ridge lies a technological giant. This wondrous sight is one of mankind's greatest achievements. This is the largest, tallest structure that has ever been moved across the face of the Earth. It can float, but it weighs more than 10 super aircraft carriers. It is taller than the Empire State Building. Here, in this Norwegian fjord, only 250 meters of the structure is visible, rising above the surface of the water. Like an iceberg, its huge bulk is submerged. This natural gas platform will soon be on the move, leaving its safe haven on a perilous route out to sea. The only channels deep enough are also extremely narrow. If at any point the base strikes rock, it will mean disaster for the skyscraper at sea. The platform's final destination is a site in the North Sea, one of the most tempestuous seas in the world. Battling against all the forces of nature, humankind seems undaunted. The urge to exploit the rich resources of the ocean floor outweigh the risks. And mistakes can exact a high price. The people who work here seek out new challenges to prove that even in these forbidding seas, mere humans can survive and prosper. Now moored safely in calm waters, this colossal structure is almost certainly the last and grandest of her kind. She is supported by 4 concrete shafts with walls nearly 2 meters thick. Soaring 335 meters up, these shafts are as close as mankind is ever likely to come to the creation of an industrial cathedral. Looking up from the bottom of this platform, the opening at the top of the elevator shaft is so far away, it recedes into a tiny square of light.
Welcome aboard. We've got about another 1,000 feet to get to the top, and I think for a single lift, that's about the longest lift ride we have in the world. And it takes us about 9 minutes to get there. Unlike most lifts, it doesn't have cables. It runs up the side of the shaft on some teeth, and that's because if we tried to have cables, they would be so long that when you stop the lift, it would bounce up and down like a yo-yo. And the weight of the cables themselves would be immense.
The Norwegians have named the platform Troll, after a mythological beast. As one of the great engineering triumphs of the 20th century, this name is ironically fitting, as this gas platform is in itself a strange realization of man's technological dreams. To build the Troll gas platform, Norsk Shell put together an international team. Frank Chapman, an Englishman, is the platform manager.
Putting a man on the moon was really the technological achievement of this century, but I really feel that we've come fairly much second to that. To put a structure this size out in the sea in the worst conditions that the globe can generate is, I think, a fairly substantial achievement.
The project began back in 1979, when a test well in the North Sea struck a huge field of natural gas in 300 meters of water, enough to supply 30 million homes with energy for 50 years. pressure to find some way of exploiting that field was immense. But so were the problems. Design engineers calculated that they would need a concrete structure 365 meters high, topped by a 100-meter high deck. But imagine the problem facing the engineers. They must build a floating structure equivalent in size to the Empire State Building that would be structurally sound enough to withstand a tow out to sea, and then a plunge into the ocean floor. A structure the size of the Troll gas platform could not possibly be built on site in the North Sea. Rather, it would have to be built in deep water at some protected site.
This is the west of Norway. It's a special place because here we have very deep water. It's more than 1,500 feet deep. And to get an idea, that's more than the mountains which are surrounding us here. These deep fjords were created up to 10,000 years ago when this whole area was covered in glaciers and these deep scours were left behind. The special thing about this fjord is that at the end of it, it is blocked off and protects us against the waves from the North Sea.
The Troll gas field lies 50 kilometers offshore, and the construction site of the platform in the town of Vats is 30 kilometers from the coast. Only along such a fractured coast as that found in Norway could a structure as deep as the Troll be built.
And of course what makes Troll very interesting is indeed its size. It needs to be developed in a water depth of 303 meters, which is about 1,000 feet, and it's going to produce something of the order of 85 million standard cubic meters a day of gas. And that's in oil terms is about 600,000 barrels a day. And to give that some perspective, into the year 2000, it will be producing something of the order of 10% of Europe's gas. A gas field of this size demands a huge concrete substructure, something like 370 meters in height, weighing 650,000 tons in weight. To give the platform its stability, there is a very large base, about 3 football fields in size. The seabed here is very soft consistency, something like yogurt consistency, and underneath this base there are skirts which penetrate more than 100 feet into the very soft seabed.
The base was built in a temporary dry dock with enough steel to build 15 Eiffel Towers. Once the walls of the base were high enough to float, the dry dock was flooded and the base was moved into a fjord. Once there, the 4 concrete shafts were poured into continuously rising forms. When the 300-meter shafts were completed, the engineers faced a risky operation, fraught with tension. The deck, which would sit on top of the shafts, had been built separately by Orca Storg. Weighing 22,000 tons, it would have been impossible to lift it to the top of the shafts, now 140 meters above the surface of the water. Consequently, water would have to be pumped into the shafts to sink the tops closer to the surface. Then, the deck, transported on barges, could be floated over the top of the shafts. The engineers knew this maneuver could prove potentially disastrous. While the shafts were submerged, the water pressure on the base would be higher than the structure would ever experience again. During the construction of the Slipner, a sister rig to the Troll, a disaster did indeed occur. In a submergence test, the shafts imploded and sank. The wreckage that hit the bottom of the fjord set off an earthquake that measured 3.0 on the Richter scale.
It happened just before we started the casting of the concrete of the Troll. We were able to receive back from the Sleipner disaster very early information on probable causes, and it allowed us then to take precautionary measures and do extensive checking of our design before we actually did any truly irreversible concrete construction work.
With the shafts sunk to their lowest point, engineers check for leaks. They find none. Anne Muir was chosen amidst fierce competition from her male engineering counterparts to manage the joining of the platform to the shafts.
When we arrived at the GBS, then it was only 6 meters above the sea and 336 meters below. And the displacement of the platform then was about 1.2 million tons. We had 1 meter clearance between the deck and the top of the shafts, and we have less than 1 meter clearance between the barges and the shafts horizontal.
With the deck positioned directly above the shafts, water is pumped out. As the shafts rise, the troll takes on its distinctive final form.
In the work, it was the best day of my life, but not privately.
It's the night before departure. The bottom of the troll's route out to sea has been surveyed again and again, but those commanding the operation cannot ignore the possibility of human error. An undetected sunken ship or an unseen boulder along the route could cause irreparable damage.
It never comes to an end. These water depths have been surveyed over and over again. But wouldn't you believe, a day before we started the tow, one of our engineers would like to have it resurveyed for a cost of more than $100,000. And I told him to forget it. But if I were wrong, that would be the end of my career.
Before departure, there is yet another concern. The captains in command require an accurate weather report before they can proceed.
Some rain show us this evening.
They know the North Sea's unpredictability and its consequence. Atmospheric lows from the North Atlantic can bring winds of 160 kilometers an hour with 25-meter waves. Wrecks of ships and oil rigs lay as testament to the North Sea's fury. The tow out will have to be called off if the weather is not favorable.
It was in a storm that the worst disaster up to now happened. 123 men died when the accommodation platform Alexander Kielland toppled over in the Norwegian Ekofisk field.
It's thought 228 men were on board when it keeled over, throwing most of them into the freezing water.
Ironically, the Alexander Halen on the left was hired at around £15,000 a day so that the men working on the main Edda platform on the right would be able to escape a major blowout. The Halen sat on its legs, each the size of London tube tunnels, with air-filled pontoons at the ends. It was held in place by anchors leading from the pontoons. And witnesses report hearing 2 loud bangs in quick succession. Events then moved terrifyingly quickly. Only about 5 minutes later, it had completely overturned.
On the basis of weather forecasts and what's going on, I think we can continue with the work.
The weather report is good, but before the troll is allowed to move, a cautious marine warranty surveyor representing the insurance company must sign off.
There you are, Helga. Thank you.
It's departure day for the troll. 10 of the most powerful tugs in the world, connected to the troll by cables, lie in a star formation around the platform. Their propellers, capable of exerting 130,000 horsepower, churn slowly. Six years, 17 million man-hours of work, and the pride of Norway are at stake. The troll will be commanded from a temporary bridge, housed in a container welded to the front of the gas platform 130 meters above sea level.
Du drar in I fjorden og så lite grann forover.
Ja, det sikkert fint det. What you see on this screen is all the small dots out here is the boats, and it's interlinked into the troll platform, as you can see here in the center.
While the troll gas platform was being built, it was anchored in place by 6 huge chains and moorings. As the chains remain attached to the base of the troll, 150 meters below the surface, the troll cannot be freed until each shackle pin is removed. It should be simple for one of the tugs to hoist each cable, lifting the pins to allow the anchor chains to fall away. But the best laid plans. To oversee the pulling of the shackle pins, a remote-operated vehicle, called an ROV, is launched. Television cameras mounted on each of its 2 operating arms allow the topside operators to see what's going on below. The shackle pins have been rusting in place for 3 years, hopefully not too long to prevent their removal. The first shackle pins pull loose with no problem. The troll is almost free. The tug prepares to pull the next shackle pin. But something goes wrong.
God damn it.
The tug deck crew have accidentally dropped the cable overboard, only to become entangled in the depths below. The ROV now has a tricky task to perform. Unless it can manage to attach a chain to the lost cable and haul it to the surface, the troll will be going nowhere. Two operators control the ROV from a portable cabin on the tug's stern. One drives the vehicle, the other operates the arms. While 10 tugs and hundreds of people wait patiently on the surface, the ROV goes about its business in exquisite slow motion. The challenge? To stick the chain hook through the eye of the cable. But when the ROV moves, the cable moves. The chain is hard to grip, and a little more slack might make the task easier. In order to do that, the operators must slide the other arm with the chain down the cable. But now the cable has twists in it. They approach the problem from another angle. Instead of trying to push the hook through the eye of the cable, they attempt to pull it through instead. So far, this proves successful. Now they must hook the eye of the chain back onto the chain to form a loop. And frustratingly, fish obscure their view. Now they must try to get the eye of the snap to open. Or try to hook the chain from underneath. After one more attempt, success. The eye of the cable can now be hauled up to the tug. For 4.5 hours, all activity on the surface had ceased.
Yeah, vi kan hjem.
The troll is at last free. The 10 tugs will tow the troll on its carefully surveyed route through the fjords and out to sea. 8 of the tugs, pulling with around 1,400 tons of force, will range ahead, The other two tugs will be hauled behind, serving as rudders. Ever so slowly, this colossal structure begins its journey.
Tug number 3, 200.
Commanding such a fleet through these twisting fjords, where strong surface and subsurface currents sometimes run in different directions, and where winds can change direction by 90 degrees in mere minutes, can never be reduced to mere science.
Tug number 4 and tug number 7 come up to power setting 6. 3, 8, 9 and 10 build up slowly your power setting to power setting 7.
The tugs are commanded by captains who, although aided by the latest electronic equipment, still depend primarily on the most flexible of computers, the human brain. Their many years of experience also prove invaluable. The men in the hot seat are the two tug coordinators who alternate the watch. They must carefully choreograph the direction and power settings of the 10 tugs to keep the troll on course. On the tug coordinator's left are the navigators who monitor the troll's course with 2 different satellite systems that are accurate to within 3.5 meters. Overseeing the tug coordinators are the watch captains and the operations manager.
Tug number 1, 145.
The tug coordinator gives each tug a separate compass heading and power setting by radio in order to balance the forces at his command against the ever-present push and pull of current, wind and inertia acting on the troll.
Tug number 10, Captain's Bridge. Captain's Bridge, tug 10.
One of the world's most powerful tugs, Maersk Promoter, leads the procession.
With the power this boat got here, with 15,600 brake horsepower and a world-breaking record on 204-ton pull on the cable, we can easily break the wire in case that we go too quick up on the tension. By this handle here, we can control the whole vessel on all propulsions and rudders at the same time. It is always prohibited for all crew to go out on the main deck due to the very big danger on the tow. As you see down here, the deck area is the dangerous area. And if a person by any means moves into that area during the towing and the tow line breaks or moves, it actually only needs to move maybe 3, 4, 5 inches, and that will be enough to kill a person.
The Troll's 322-kilometre voyage to the North Sea will take it on a winding route through the fjords. At about 1.5 kilometres an hour, the passage should take 6 days, but obstacles abound. The first test comes only a few kilometres after setting off. The Troll must take a hard right as it leaves one fjord and enters another.
All tugs 20 degrees to starboard.
Although the captains have studied the towing route of the Troll in a simulator, no one knows exactly how the Troll will behave in a real turn, or even if it's possible to keep it on a deep water course through the fjords.
As you can see, we have started the turn quite early on. The reason for that is that we got the wind coming in from that side, so we want to be a little bit ahead. You can see the lines here. All inside that air is survey air, so we are still safe.
The tow is so stable. It is going excellent on the track. It's going even better than we experienced on the simulation we were on. So we are very happy with that.
Almost immediately, another challenge presents itself, testing the ability of the tug coordinator to hold the Troll on course. The underwater channel begins to narrow.
Navigating this 39 nautical miles out of the fjords has been quite a hazardous operation, since in places the channel, although it looks wide here on the surface, underneath in places is only twice as wide as the base of the structure.
The information the navigation system is giving is vital We are now seeing the Troll platform towing south of the Vinda fjord. We can see the 10 tugs, 8 in the front and 2 in the back steering. And this is the outline of the skirt tip of the Troll platform. And here we can see the critical depth curves, 240 and 250 meters, to keep clear of the critical depth.
We have to be careful with the underwater part of the hull. Make sure that it doesn't hit any rock or any shallow spot.
The crew on the Troll must cover all possibilities. If the platform's skirt collided with the side wall of the fjord, the result would be catastrophic. Once a crack opens in cement, the fracture could widen and travel, fatally weakening the entire structure. The Troll engineers have meticulously planned to avoid such surprises. But at the same time, they have to be prepared to deal with a catastrophe. On the trip out, only 22 people are permitted on the platform at one time. The maximum number the ever-present helicopter could lift off in one flight. If Troll did strike a rock and crash, a very brave or a very frightened man might even trust his fate to a very thin evacuation tape. But it's a long way down. The mountains on each side of the fjord loom closer as Troll enters the area in which he will be most at risk.
Here we have all the information we need to move the platform along the desired track. The critical depths we have 240 meters. We're not supposed to touch those.
Carefully and exactly on course, Troll is towed between the underwater canyon walls. Thankfully for the men on board, Troll passes safely through the narrows without incident.
There are very many challenges to be faced, and when you're actually underway, you can meet new hurdles and challenges and things as you go along. After we'd started the basic engineering of the deck, when we were in the very early conceptual stages, we had the very unfortunate Piper Alpha disaster in the UK when there was great loss of life offshore.
Troll was one of the first projects to come after that disaster. So one of the things that we did immediately was to try and look for ways of reducing the destructive force if you were to have an explosion. And in order to do this, we made models that were about 1/12 the real size of the production modules and the wellhead modules. And we took these to the Pennines in the UK, and we conducted a series of 80 explosion tests there. And the thing that we did was to choose a very long, thin layout so that this safe haven of the living quarters is very much separated from the hazardous wellhead process and export areas on the platform. We've also put multiple barriers in here in order to get fire barrier and an explosion barrier between the respective areas, so therefore compartmentalizing, if you like, the hazardous areas.
It's the second day of the tow. The arms of the fjord widen towards the open sea. No longer hemmed in by mountains and narrows, Troll takes to the element for which it was designed. Yet another navigational hazard lies ahead on the route to the gas field. Troll draws 229 meters. A reef on the route is only 9 meters deeper. Troll should pass over the bar safely, but if sudden high winds cause Troll to tilt, her skirt could strike bottom. As Troll advances into the shallowest part of the reef, there is just 12.5 meters of clearance under the 460-meter structure.
11.1.
It's now 11 meters, even shallower. The insurance representative can call off the attempt if he foresees imminent danger.
You can see from the drawing there that we're just about halfway across the shallowest part of the tow route.
10.9 now.
Yet shallower at 10.5 meters. Finally, Troll passes the red lines into deeper water and safety.
It's very good. They have some 10-meter clearance.
It went well. There was no surprises. We're all very happy.
Oh, I feel great. Yeah. Everything is just out according to the book.
For 7 years, the design engineers have had many sleepless nights worrying about what could happen during the crossing of the bar. Now the passage has been accomplished without incident in just 1 hour. Now in deeper seas and 4 days into her voyage, ballast engineers begin letting water into the air-filled chambers of the Troll. The platform's slow and carefully monitored descent into the depths begins even before it reaches the gas field.
We're now getting ready to start descending the platform.
Is that?
About 60 feet. We're doing this when they still are towing the platform, and this is the start though to put it on the bottom of the sea.
The connecting span, or regal, now just skimming the surface, will be the first structure to disappear from sight.
430 feet below us we see the regal compartments. We are just about to ballast these ones and submerge them. We are probably the last persons in the world looking at that regal before it will be submerged, and that's something.
24 hours later, the regal has completely disappeared beneath the waves. Troll now floats 30 meters lower in the water.
Here we are now, and the platform's just about getting ready to start the installation. The wind's dropping and the waves are subsiding. So with a bit of luck, we should be, by about 6 o'clock this evening, able to start the penetration.
At 1500 hours, we got permission to move in and go straight into the location. In about 1 hour, we'll probably tack bottom here on this location where this huge platform have to stay for the next 70 years.
Take 750.5.
The game has now changed. The tug coordinator is maneuvering his tugs into a star pattern around the Troll. As the gas platform sinks towards the bottom, he must try to hold it in place over a predetermined position of only 100 meters across. As long as the weather cooperates, the descent will continue. Once the Troll's skirts have penetrated just 1 meter into the clay, its position can never be changed. The plotter displays the relative position between the multi-sided Troll and the circular area onto which it must be centered.
Now have a clearance to the seabed of about 20 centimeters. We are just adjusting the position.
A touchdown anywhere within the 100-meter wide outer circle is acceptable. The target is the inner circle.
We have just came to touch condition on the port side of the platform, and we have now penetrated 10-15 centimeter. And the position looks very good at the moment, so we are ballasting down, continue ballasting down. But for the moment, we are in touch on 2 places, and we are approaching touch on the 3rd place. It shouldn't take long before we have touch all around the platform.
A little sad because now it's going to the end of the project.
Troll is now irrevocably committed to a permanent position on the Earth, just 5.5 meters from the exact center of the target area. During the next 5 days, the great weight of the Troll forces the skirt 36 meters down into the ocean floor. In her final position, the deck is 30 meters above sea level. There she will be joined by a floating hotel.
We're putting together the final parts of the platform and hooking it up, and so we need to accommodate somewhere around about 600 people offshore. And we bring offshore then this thing down here, Flotel, sort of like a minor town or city where we accommodate everyone, feed them, look after them whilst they're working off here.
This vessel is able to perform technical triumphs in seamanship 24 hours a day. It's not anchored, yet it maintains a precise position next to the Troll. Battling against high winds, strong currents and gigantic waves, 6 thruster propellers controlled by computer hold the floating hotel within a few meters of the Troll, never allowing the 2 structures to collide. They are connected by a telescopic walkway.
We tend to take it for granted, people walking across the walkway and working as normal, but of course this thing's under the influence constantly of current, waves, wind. It's constantly wanting to shift, and we reckon we can be here with waves up to about 20 feet and stay on station the whole of the time.
Aboard the platform, business is about to begin. 40 wells will be drilled just over a kilometre into the gas-bearing sandstone. The destination of the gas is a giant treatment plant based at Kolsnes. From the North Sea field, the gas must first be piped ashore under extreme pressure to the terminal. Positioned on the seabed, it lies at the base of a rock wall not far from the coast. Moving the gas from the terminal up the cliffs of the continental shelf to the treatment plant has proved an enormous problem. No pipeline could endure the harsh conditions presented by the igneous rock found on Norway's craggy coastline. Some other solution had to be found.
The first challenge we have as a pipeliner is how do we connect the platform to the coast where the gas will be treated. It is impossible to build pipelines on rough rocks and rough terrain like this is. So we have a huge challenge. How do we get from this point to the shore, to the station where the gas will be treated? We have to make a tunnel from Kolsnes down to this part of the seabed, and we then make a hole in the seabed.
In 1991, as the Troll shafts were being built, the tunnel that would connect Kolsnes with the ocean floor was already under construction. A giant ventilating tube would provide fresh air for the workers at the bottom.
Right now we're driving down to a point which is approximately 700 feet below the sea level, and as far out as 2.5 miles under the North Sea.
The engineers were then faced with a unique challenge: to find a way of connecting the pipeline in the tunnel to the gas pipeline coming from the Troll field. This would involve drilling from inside the tunnel through to the sea floor, a seemingly impossible task to undertake without flooding the tunnel.
If you calculate the pressures that work on that little bit of rock that is still separating you from the sea, they're fantastic. The total force is something like 7,000 tons. To make the penetration between the tunnel and the sea, we fit the shaft out with concrete lining and already prepared a support that was going to be used later for supporting a big concrete plug. We then shielded the shaft bit off by building a big 8-meter concrete plug in the tunnel, a couple of meters from the vertical shaft. And then we prepared final blast, the penetrating blast between the sea and that vertical shaft. Two guys here in the tunnel, they lighted the fuses and waited for the things to come. Everybody else was out of the tunnel, of course, when the last penetrating blast was set off. So then the shaft was flooded, but of course the tunnel could not be flooded. The concrete plug was sealing it. Then with a big crane we lowered a prepared concrete plug with pipeline ends sticking through it. That was lowered onto this prepared seat in the vertical shaft. And it was grouted up. After letting it cure for a couple of weeks, we very carefully opened a little tap to see if the pressure behind the plug was dropping. And yes, it did. That meant that we could drain the area behind the shaft, remove the plug, and from there on we could construct the pipelines in the tunnel.
While work at the tunnel was well underway, an entirely different project had begun only a few kilometers offshore. A chartered vessel, the Castoro Sea, set about laying down the two pipelines that would convey the gas from Troll to the treatment plant at Kolnes. From there, a network of pipelines will convey the gas all over Europe. The 150-meter-long Castoro Sea acted as a floating factory. Mounted on top of 10 shafts supported by 2 submerged hulls and secured in place by 12 anchors, each weighing 22 tons, the vessel trailed out pipeline by slowly winching forward on her anchor cables while letting out the cables astern. On average, Castoro Sea was able to lay 100 sections of pipe a day, adding up to 2.5 kilometers to the pipeline daily. Work on the pipe-laying vessel never stopped. The 300-strong crew was able to keep the assembly line going 24 hours a day. Every 15 minutes, another length of the pipe was ready to be launched. The barge was pulled ahead on its anchors and another section of pipe committed to the sea. At this rate, the pipelines to shore were soon completed, ready to transport the natural gas from Troll and aptly timed to coincide with the first drilling. Traditional drilling decks such as these are regarded as one of the most dangerous working areas in the industrial world. The men, roughnecks as they're called, must wrestle with equipment weighing tons to move thousands of meters of pipe and casing up and down. Hands and limbs, torsos and heads are constantly in harm's way. On Troll, however, the drilling operator is protected by a screen.
The way we do it is that we are drilling through the cement down, 360 meters below us, and they're drilling through the cement and into the seabed.
The movement of pipes on the drill deck is almost completely automated. But in oil and gas production, there is always an edge of danger. When the first well is drilled, it is possible that it could run into a pocket of what oil men call shallow gas.
If we hit shallow gas pockets, that can create a dangerous situation with gas flowing outside the well and beneath the platform legs and start caving out the soil beneath the legs. And we'll do everything to prevent that situation.
Under such tremendous pressure, shallow gas could escape not only through the well casing, it could also leak out around it. Gas enveloping the platform could easily ignite. or so pulverize the clay under the troll that the base would collapse. In gas fields, this kind of catastrophe has happened in the past. A shallow gas fire could destroy the best laid plans of these dedicated engineers and a multi-million-pound structure. But thankfully, the Troll's first wells go down without complication. This modern-day colossus, acclaimed by some as the 8th wonder of the world, is now firmly in place. For Frank Chapman and the thousands of other workers who have given years of their lives to designing, producing and moving the Troll, it is time to depart. They can leave with quiet satisfaction, knowing that it's unlikely that this skyscraper at sea will ever be equaled. Even as Troll was being constructed, lighter floating drill platforms for oil and gas wells were already in development. Troll is therefore not only the largest concrete-based platform ever built, it is also the last of the giants. The construction and tow to sea of the Troll must be high on the list of the greatest industrial achievements of the 20th century.
Next night, a doctor is found unconscious in Central Park and a man jumps from the 7th story of a building. Trauma, life and death in the ER follows.